Thank you for the introduction. Good. So I think the worst part is over. I took off my jumper. It's freezing. I say it again. And I promise I will be quick because I'm standing between you and lunch. So today I'm presenting this next step. So it's follow-up of a series of presentations we already done in 2017 at GPD and at Challenging Glass in 2018. So it's the latest development in this research work that has been going on since some quite time. So between the first structural glazing project in the 70s and the writing of the ETAg, the buildings were not as ambitious as we have just seen with Agnes' presentation. And the average wind load was at 1,500 Pascal, and that was already quite exotic. So when the ETAg guideline was written in 1999, it was really built on those buildings of the time. Limited glass size, limited deflection, and wind loads. So it was possible to develop a calculation method that was fitting with those projects. And a number of simplified assumptions were made. For example, we said that the wind load was low and the deflection of the glass pane as well, and so that you can assume the joint working mainly in tension, and the rotation was neglected because, of course, there's always a little bit of deflection, but they decided not to take this into account, and they assumed a homogeneous stress distribution along the bight, whilst along the frames it was heterogeneous. They also assumed that the joints would stay with the aspect ratio between 1 and 3 because it was known at the time that the movement capacity of such joint geometries is good enough to accommodate the movement. And by performing a very simple balance of force, it's possible to derive this famous equation that gives you the bight as a function of the small panel dimension, the wind load, and the design strength for the silicone. They used a very large safety factor, if you compare, of course, with safety factors used in other industries, to cover for all these simplified assumptions of the calculation, to cover as well for manufacturing tolerances, and to cover for natural aging. Even if silicone is a very performing technology, there is a slight aging happening. Today, we are dealing with those nice buildings. The wind load is, of course, more 5,000 Pascal. The glass pane dimensions are huge. And we are seeing deflections that typically will not be at 1% or L over 100, but above that. The ETAg equations are not valid, while the boundary conditions to have it valid are not respected anymore by customers. And even if customers want to apply it, typically this high wind load will result in a joint that is economically and aesthetically not pleasing. So customers are looking for alternatives. They search to apply finite element analysis, but as well there's a need to provide an alternative equation calculation method that will take into account all the effects that were neglected previously, including the rotation, and looking at the effect of the glass pane deflection, the influence of the modulus of the joint, so all factors that were not in this simplified balance of force. So we propose a new equation that takes this into account. On the top, you can see the full equation that takes into the relationship, the hyperelastic character of the silicone. And on the bottom one, the second one, is a more intuitive, more comprehensible equation. So we have the original term here from the ETAg equation, and we have a new term. That one includes all the aspects that I described previously. So we have the influence of the joint aspect ratio is taken into account by a factor that we call the rigidity factor. We have the Young modulus that influences as well the strength of the sealant and its capacity to hold the loads. We have the bight and the thickness. So the thickness was not in the ETAg equation, whilst we know that it has a real influence on the joint movement capacity. And we have the rotation angle of the glass. And the rotation angle is actually influenced by the bite dimension, and larger bites can have a significant reduction of the deflection. So the homogeneous stress, the stress that we had with ETAg, will decrease with increasing bite, but you can see as well that as you increase the bite here, you're also increasing this term. So the rotation stress here will go up as you increase the bite. So there's a balance to be found, or there's an equilibrium to be given back by increasing the thickness. If you increase the thickness, then you can keep this rotation stress under control. So we have performed quite extensive validation of this equation on a finite element analysis basis, as well on H pieces. But safety is one of our major concerns at Dow, and we are now looking at validation at larger scales to make sure that all the conclusions can be extrapolated to the facades we are dealing with. And so this is really the topic today, is to give you an update on the latest state of these validations. So our first trial was not so successful. We had the ambition to, to test here a 1 meter by 1.5 meter or 3 by 5 feet in this setup. So a classic air pressure test. Now we are very cautious, so it was not glass, it was an aluminum plate, but with a certain thickness to mimic behavior of glass. And we used 983, so all these tests have been done in the US, which is also a nice way to validate that the formula that we proposed that was validated for 993 on H pieces is also extrapolated to other silicones as well. We used it and tested after full cure, but unfortunately our equipment is not able to break the system. The air pressure in the test unit was not enough. So we had to go back to find an alternative way to validate our equations on a large scale. And we thought about using an indentation test. So it's basically a pressure test. So we have really mechanical pressure in the center of our panel. We are using a hydraulic actuator, and we measure the forces at the same time. And the benefit of this setup is that we can go at a much higher force. So you can see here that we go back to slightly smaller dimensions. We are here at 30 by 30 centimeters, or 1 feet by 1 feet. So you see here, these are steel frames, so extremely rigid, no deformation. So this is really mimicking what we model. So when we do a model, we always assume perfectly rigid frame conditions, which is, of course, not reality, but is focusing on the behavior of the silicone. We verified that this indentation test would be able to provide the same levels of strain as we expect with pressure loading. So we used Abacus with Mooney-Rivlin system, material system for the 983. And you can see that we reach in both cases similar values for the strain, so that was validated. And we also can assume that on that scale, the failure strength would be the same as for an H piece. So based on that, knowing that 983 will fail eventually at 1.1, 1.2 megapascal, we can calculate how much force is needed depending on the joint bite dimension. So we see that we are in a range of 24,000 Newton. Here we can reach that with our system. So then we went ahead and we prepared samples. We did use 3 aspect ratios, 6 by 6, 18 by 6, and 24 by 6, so an aspect ratio of 1, 3, and 4. It's aluminium bonded to a steel frame and perfectly rigid, as I said before. And on this slide, you can see how the test looks. So as you push and as you increase the indentation displacement, you will eventually reach failure. So we can see on this slide, as how the force increases to reach the maximum. Then we have a first failure. We push again, second failure, further failure, until final failure here. So the peak force to break was about 6,000 Newton. And if we check the predicted indentation force with the FEA, we were very close with the measured value. So as you see here, what we also observe with the FEA is that this joint of 6 by 6 is mainly acting in tension. The test is repeated for the different aspect ratios, so 18 by 6, similar observations. So we have a peak force about 12,000 Newton here, and the prediction from the FEA, so our material model, is very, very good because it's predicting our experiment. We reach failure, and the peak strain is observed near the inner edge of the SSG, and this is where the failure happens. The way the joint starts to deform is more into adding a rotation component due to the larger aspect ratio of the joint. Same for the 24 by 6, but what you observe here is as you continue to increase the bite, you do not continue to increase the maximum force that is needed to break the sealant. So we have reached an optimum value of bite, and increasing further the bite will not help to increase strength and safety. Here again, you can start to see here that there will be a slight compression there, and here the rotation component that is more important. So if we compare the peak strength as a function of the bite design, we see that we were at 6,000, going up at 12,000, and then down again as the bite increases. And as well, the strain in the bite will not continue to decrease. We stabilize here. And so this is really in correspondence with what was observed in H pieces previously. Same, if I put the 3 deformation modes next to each other, you observe the difference in deformation that is influenced by the aspect ratio, and we can see that the tensile strain is really always concentrated near the inner edge due to the rotation. As we see those results, I think it's evident that there's no point at a certain moment to continue to increase the bite. We need actually to increase the thickness as well, and there's an optimum to be reached. There's probably a joint volume redistribution that will need to be done, working less on the bite and more on the thickness. But still, that is to cope with exceptional wind load events, and it's important not to reduce the bite too much because, of course, we have daily fatigue and movements that need to be accommodated. So then comes the question, what's next? And actually, as we are really focused on safety, and this is not large enough, it's only 30 by 30, our focus is still to break a large scale. Well, this is only a medium scale, I would say. So it's 1.4 times 1 meter, and you can see that we have drastically changed our setup to be sure that we can break the bond. So we are bonding it on the floor, so here under the aluminium plate, and we have an air supply into the aluminium plates. We are using here a frame that is even reinforced to ensure that we are not going to deform, because at certain pressure that can happen. And eventually, I hope we'll come back with a final conclusion on what our recommendation will be for bite and thickness design. So that's it. Thank you for your attention.
Thank you, Valérie.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.